We're going to skip lesson number 6 because, as you can see, lesson number 6 is just going further into factoring polynomial expressions, and these examples in lesson 6 are enrichment for us who are following the Alberta Program of Studies, and so this is above and beyond what the scope of Math 30-1 is required to teach, and so we won't worry about that lesson. We're going to skip right over to lesson number 7. We're going to talk today about the graphs of polynomial functions. We're actually going to do part 1 and part 2 both today because they're very short and a lot of it is review from Math 20. So just as a really quick review at the top, when you hear the words zeros, roots, and x-intercepts, those just all mean the exact same thing. So when we're talking about it in terms of a function, it's the zeros of the function. If you're being asked to find the zeros, it's the same thing as if you're being asked to find on the graph the x-intercepts, the points where that graph crosses the x-axis. And if it's in equation form where y equals 0, then you're being asked to find the roots of the equation. But those things all are the same numbers. They mean exactly the same thing. Okay? Today we're going to talk about unique factorization theorem, and what that really means is just that every polynomial function whose degree is greater than or equal to 1 can be written as a product of a leading coefficient, that's this c here, and a certain number of factors. And as you can see, it goes on and on and on and on. Okay? So this theorem actually implies 2 important points, and really this is nothing new. This is all just a review. So if you have a highlighter, please grab your highlighter, and we'll just highlight these 2 important points. The first one is that every polynomial function can be written as a product of its factors and its leading coefficient. Okay, just like we were doing yesterday when we were factoring polynomials, that's exactly how we wrote them, was as a product of their factors and a leading coefficient. In many cases is 1, but sometimes you'll have a leading coefficient there. As long as your leading coefficient is greater than or equal to 1. And then the second point is every polynomial function has the same number of factors as its degree. And these factors can be real numbers or complex numbers, and they can even be repeated factors, and you're going to see today what that means. Okay, so this should make sense that every polynomial has the same number of factors as its degree. This means, for instance, if you had a polynomial that was x to the 4th plus 3x cubed, and on and on and on it went, this means that the highest degree of x, which is the 4th power here, would mean that this particular polynomial equation has 4 factors. And that should come as no surprise to us, because when we have factors that are being multiplied together, if you had 4 factors that were all x plus or minus something, and you multiplied those together, that's how you would get x to the 4th, right? So it does make sense that the degree of the function dictates the number of factors that would be in that. You would be able to split that polynomial into its factors, and that's how many factors you'd get. Okay, let's have a look at class example number 1. This is a graph of x cubed minus 2x squared minus 5x plus 6. We're going to use the graph, it's given us the graph, to state the zeros of the polynomial. Well, the zeros are just the same thing as saying the x-intercepts. We can read those right off of the graph right here. Okay, so our first x-intercept is -2. The 0 of this function would be -2. The middle one is 1, and the one on the far right is 3. If we have to state these now as factors, -2 as a factor would be x plus 2, right? And 1 as a factor would be x minus 1. And 3 as a factor would be x minus 3. Okay, so then in final form, if we had to write this polynomial in factored form, we would write it as polynomial as a function of x is x plus 2 times x minus 1 times x minus 3. Okay. Now we can use a graphing calculator to sketch this graph in its expanded form, which means in this form here. If you plugged all of that in to your calculator in y1, you would get this exact graph here, passing through x-intercepts of -2, +1, and +3. Okay. Then if you plugged in to your y2 the factored form, which is this form here that we just came up with, you should, and then you asked me this time for a thicker line so that you can differentiate between the two, you would get this exact same graph passing through x-intercepts of -2, +1, and +3. Okay, and you could do that just to verify your answers. Okay, let's have a look at class example number 2 on the second page. We're going to use a graphing calculator to sketch the graph this time. So if you would plug into your calculator into y1 this equation here, this function here, and then once you get it, sketch it on the graph given. Just pause the video so that you can do that, and then resume it again as soon as you have done that. Okay, you should have had a graph that passes through like this, something like this. Okay, we'll put arrows on both ends. The x-intercepts that it passes through are -2, 1, and +5. Okay. So if we use the graph to state the x-intercepts are -2, 1, and 5. Write the polynomial in factored form. Well, that's pretty simple now. This should be coming more naturally to you now. If our x-intercept is -2, that's a factor of x plus 2, x minus 1, and x minus 5. Okay. All right, now looking at our graph, we have to circle the correct alternative. The left arm of the graph, that's this part of the graph. This part is what we call that rising on the left, okay? The right arm of the graph, that's this part, is falling. The degree of the polynomial, the highest exponent of your leading coefficient, the exponent of your leading coefficient, or the highest exponent in all of your x's. If they're in mixed up order, you'd have to rearrange it and put it in descending order of powers. So the highest power is cubed, so this is degree that is odd. X cubed is an odd degree. And the leading coefficient, our leading coefficient here is -1 really. And so this is leading coefficient is negative. Okay. I'm going to give you a little bit of notes here to add in your margins that will just kind of explain about the general shape and what quadrants graphs will always start and end in. So in this margin over here, if you would write that even degree, polynomial functions of even degree, and what do I mean when I say even degree? That's like x squared, x to the 4th, x to the 6th, and on like that, okay? These types of functions that have an even degree, if the leading coefficient is positive, they will always follow, they will always start in quadrant 2, they will go down, but they will always end again in quadrant 1, okay? Now, they'll have different shapes. This function here is degree 4. Degree 6 would have more squiggles, and as you know, quadratics, degree 2 would only be the shape of a parabola, so it would not have this middle section that makes it look like a W. Okay, so the shape will be different, but which quadrant it starts in and ends in will always, always, always be the same. Okay, so if it is a even degreed polynomial, it will always, always, always start in quadrant 2 if it's a positive leading coefficient. Okay, if it is a negative leading coefficient, then you would have your graph would start in quadrant 3 and end in quadrant 4 if the leading coefficient was negative. Okay? Always, always, always. Okay, on this side, let's make a note then about polynomial functions of odd degree. These would be your polynomial functions that are x, or x cubed, or x to the 5th, and so on. Okay? These ones, of course, will again have different shapes, but they will always have the same beginning and ending behaviors. Okay? So if it is positive leading coefficient, then these graphs will start in quadrant 3, but they will end in quadrant 1 if your leading coefficient is positive. The same is true if your leading coefficient is negative, then they will start in quadrant 2, but they will end in quadrant 4 if the leading coefficient is negative. Okay. Now there are some questions here for you to do, questions 1, 2, and 3. This was a very short lesson, and hopefully much of it is review. Questions 1, 2, and 3 will just help you get some practice with writing polynomials in factored form. And we'll move right on to lesson number 8, and then you can come back and work on those questions at the end of the class time, okay? So if you would flip over in your books, please, to lesson number 8. We'll do part 2 as well. Okay, so here is the graph of a polynomial function, and this function, because it is the shape that it is, shows us that this is a function of degree 3, because if it was just a parabola, it would be degree 2. If it looks a little bit like a W or an M, upside down W, then it would be degree 4. This shape here is degree 3. This is a cubic function. Okay? Now, that makes sense because if I multiply these factors out, I really got x plus 1, and then this is really x minus 3 times x minus 3. Right? So I have 3 factors here, x plus 1, and then x minus 3 times x minus 3. One of those factors is repeated, but it still is there twice. And so if I multiply this out, I'm going to end up with x cubed and a whole bunch of other things. Okay. All right. So this says this polynomial has 2 factors that are different, unique, and different. One of those factors is repeated, and that's what this squared sign right there tells you. The x minus 3 is repeated. This means the function actually has 2 distinct zeros. It will pass through the x axis in 2 distinct points, -1 and +3. Okay. And one of those 2 distinct zeros is a repeated 0, okay? And that is +3, this one right here. Right? Because that's the one here that is being repeated. So the factors of this equation are x plus 1 and x minus 3, which is repeated. The zeros of the function are 3 repeated and -1. And this graph has two different x-intercepts, so we just say that it has two real distinct zeros, -1 and 3. Okay, this point of repeat where this graph touched the x-axis at 3, but it didn't actually pass through it, is very important. We call this multiplicity of 2. We say that this repeated 0 of 3 is a 0 of multiplicity 2, which means it's being multiplied by itself twice. That's what we see in this original equation right here. Multiplicity 2. This other factor, x plus 1, only has a multiplicity of 1 because it's only a factor once. X minus 3 is a factor that is repeated twice. Okay? So multiplicity just tells you the behaviors of a graph so that you know whether they will pass through the x-intercept, or sorry, the x-axis, or whether they will just touch it and then bounce away from it, or whether they will pass through it at a point of inflection, which is just a slight curve. So we'll talk about what multiplicity really means. Okay, we've got a few notes here that we're going to make in this spot. So multiplicity really just affects the behavior of a graph. What the line does. Okay, and here, this statement here is very important. The multiplicity of a 0 corresponds to the number of times a factor is repeated in the function. Underline or highlight that sentence. Okay, so we're going to take a few notes, just kind of, you don't have a whole lot of space in this spot, so maybe we'll take a little bit in the left margin and a little bit in the right margin. Okay, so if you have a graph that has no multiplicity, and what that really means is multiplicity of 1. In other words, that factor is not being repeated, it's only in there once. Okay, what that means is that the graph will pass through the x-axis at that point as a straight line. Okay. Then on the other side, we're going to talk about odd multiplicities and even multiplicities. Okay, so the first one we'll do is odd multiplicities. And what we mean when we say that is multiplicities of, obviously not 1 because that counts as no multiplicity, it's just in there once, but multiplicities of 3, of 5, of 7, or on and on and on, okay, where that same factor is being repeated 3 times, in other words it's cubed, 5 times it's to the 5th power, 7 times it's to the 7th power, okay. When that happens, it passes through x, the graph passes through x, through the x-axis at a slight curve, and this is called a point of inflection. But it does pass through the point. It curves, it changes direction a little bit, but then it continues going in the direction that it was going. Okay? And the last one is even multiplicities. And this is where we're talking about multiplicities of 2, 4, 6, on and on. So factors that are squared or to the 4th power, to the 6th power. Okay, so this is where the graph bounces, like the graph touches the x-axis at that point. But then bounces off. And never passes through. And this is known as a tangent. Okay, so the next section just kind of gives you a visual of what that would look like. Okay, so a polynomial graph is tangent to the x-axis at a point where the graph touches the x-axis. So it comes here, it touches the x-axis, and then it doesn't cross through it, but it kind of bounces off of it and continues back in the direction that it came from, more or less. And you can have that either up or down. Okay, so it never actually passes through the x-axis, it just bounces off it. A point of inflection, however, is a polynomial that would actually reach a point on the x-axis right here, and then it gives a slight curve, and then it continues going up. Or if it's coming down, it does the same thing. It touches the x-axis at that point, slight curve, point of inflection, that's called, right there, and then it continues going in the same direction it was. Okay? All right, so let's have a look at the next page and see if we can put this into practice. Consider the polynomial function that is a polynomial of degree 6. See how the highest power is 6 if we put this in descending order of powers. And so we know that this is a polynomial of degree 6. They have been very nice to us. They have factored it here for us. But I can see that I have one factor that is being used once. That's my x plus 3. I've got x plus 2 that is being repeated twice. And then I've got x minus 2 that is being repeated 3 times. Okay? If you use your graphing calculator to sketch the graph of this, make sure that you set your windows using this. Pause the video for a minute. Plug in either the expanded form of the polynomial function, or you can plug in the factored form, it doesn't matter. And set your windows for these settings. Graph it, and then start the video again, and then we'll continue the lesson. Okay, when you did this, you should have got a graph that looks something like this. Okay, it would have passed through -3. It touched -1, but then it bounced away and did not pass through it, and then it passed through +2 at a point of inflection where it changed direction with a slight curve, but it continued going upwards. Kind of a funky looking graph. All right, let's see if we can fill in the chart. To state the zeros of the function, their multiplicities, that means how many times they're repeated as factors, and then what that actually means, where it says description, that just means what is the behavior of the graph. Okay, so we have 3 zeros in this case. That's 3 points where the graph touched or passed through the x-axis, one at -3, one at -1, and one at +2. Okay, so we'll fill those in here. -3, -1, +2. We can read those from our factors here as well. -3, -1, +2, right? Okay, now the multiplicity of the 0 that passes through -3, we can look right here. That's this one. It is only being used one time, so we say it has a multiplicity of 1. When that happens, that's like no multiplicity. It's not being used repeatedly. Multiplicity is how many times that factor is being repeated. It's not being repeated at all. And so what that tells us is that it passes through the x-axis at -3. Right? And that's the behavior that we see the graph following. Okay? Then at the point -1, that's this factor here. It has a multiplicity of 2, which means that factor is being repeated twice. And when that happens, when you have multiplicity 2, that's an even multiplicity. That's that point where your graph's going to approach. It's going to touch at that point, but then it's going to bounce away and not actually pass through. So we call that tangent. So it's tangent to the x-axis. At -1. And then we have the last factor here, which has a multiplicity of 3. That means that x minus 2 is a factor 3 times in this equation. And so it has a multiplicity of 3. That's an odd multiplicity. And so this is where you have a point of inflection. It'll pass through at that point with a slight curve. That's called the point of inflection, where it kind of changes direction a little bit, but then continues going on in the direction it was going originally. Has a point of inflection at 2, +2. Okay, now the degree of this polynomial is degree 6, right? We looked at that earlier, and we saw that that was the highest power in this equation, so that is our leading term. And so that tells us what the degree is of this polynomial function. It's degree 6. And the cool thing about this is the sum of your multiplicities of the zeros is also 6. Okay, so what that means is if you added up your multiplicities here, 3 plus 2 plus 1, that would give you 6. Okay, so a polynomial function of degree 6 will have 6 multiplicities. If it's degree 3, it will have 3 multiplicities. They will always be the same. Okay, you can use your technology to determine to the nearest tenth the minimum value. This is just where you would plug in or look at your graph, which you plugged in a minute ago into your Y1, and you would just ask it to calculate the minimum. That's the lowest point on this graph. If you look back at this graph, that's this point, right? That would be our minimum point. You're wanting to know what that value of y is at that minimum point. And if you do that, you'll find that the minimum point is negative 102.5 to the nearest tenth, it said. All right, class example number 2. A polynomial function has this equation. Okay, first of all, what's the degree of this function? Right, it's degree 4. So we would expect it to have how many multiplicities then? 4. Right, let's see if that is indeed the case. Okay, so again, you're going to put this function into your calculator in your Y1. Adjust your windows using these settings so that you can see it. Well, stop the video until you've sketched it, and then turn the video back on once you're ready to continue the lesson. Okay, your graph should have looked something like this, where we're passing through the x-axis at -4. We have a point that is tangent at -1, and we have a point that we're passing through again at 4, +4. Okay, so we can fill in our zeros. We have a 0 at -4, we have a 0 at -1, we have a 0 at +4. Now this time, they haven't actually factored this equation, but we can tell just by looking at the graph what the multiplicity would be, okay? So if it is passing through the point at -4, that's multiplicity 1, right? That means really that factor is just being used once in this equation, and the behavior then passes through the x-axis. At -4. Okay. Then at the point -1, what do we see happening here? Well, the graph bounces up, touches it. There's a tangent point, but it bounces back away, right? At this point of -1. So when that happens, that's a multiplicity 2. That's an even multiplicity if it has a point of tangent. So it is tangent to the x-axis, touches it, but doesn't pass through at the point -1. Okay, and at the point 4, what is happening again here? Well, continues up, passes directly through with a straight line at the point 4. So that's, again, multiplicity 1 then. If it's passing through the point, passes through the x-axis at +4. All right, so the last thing it asks us then is, if we know our zeros, right here, and if we know the multiplicities, that's how many times they're being repeated, we should be able to write the polynomial in factored form. Okay, so what that means is we have our polynomial in x, okay, our first factor, okay, the factor that would go with the 0 that passes through -4, that would be x plus 4, right? And how many times is it used? Once, okay? Now we're going to do this one. This is x plus 1. How many times is it being used? Squared. And then we're going to do this one. This one is x minus 4. And how many times is it being used? Just once. Now, we don't have this quite in the form they've asked us to put the squared one at the end, so we just need to rewrite it, rearranging it so that we have x plus 4, then x minus 4, and then our x plus 1, which is the repeated factor, the point of tangent, where it bounces off at the very end. Okay, so this would be our final answer. Okay, you also have an assignment that goes with this section. And again, we're not going to do all of those questions, but question 1, 2, and 3 are very good practice. So let's do 1 to 3. We'll do 5 and 6. 7. And number 13. Okay, and that will be good for today. So don't forget to go back and do the questions 1, 2, and 3 from the previous lesson, as well as these questions from this lesson.